Hello everyone. In this example, I'm going to compare three types of cache mechanisms: direct map, two-way set associative, and fully associative. For the purpose of this example, I'm going to use only a cache with 4 blocks available to store data. And I'm going to use a sequence of 5 requests only for the purpose of the example. The request will be 08068. And for just for this example, I'm going to assume I have 2 to the 5 memory locations available for the computer. So this is going to reduce the size of how many bits we need to give addresses for the memory. Okay, so let's move on to our examples. The first example is uh, direct map memory. So we have 4 blocks and we can store 1 word per block. If you remember in the given case, we have 4 blocks available. That's why we can have 4 indexes. Okay, so the first thing to do here is by value, I would be writing the binary versions of all of these given requests. So 0 would be 00000. 6 would be 00110. 8 would be 01000. Okay, so why do I have spaces in between uh, these zeros or 1 and 1 and 0 and 0 here? The reason for that is, if you remember, I have 2 to the 5 memory locations. That means my addresses will be 5 bits. And when I look at this given specific example, I have 4 different blocks available for me to index. So the indexes that we write are the last 2 bits of the memory address. So for example, if I am going to use 0, if I'm going to use 0, 0 has to go into index 00 here. And the tag for this is going to be 000, the first 3 bits. If I'm going to put 6 here in the cache, it always has to go into 10 here in the index, and its tag would be 001. All right, so we just look at the indexes, and index is the last bits. All right, so let's start our example. Okay, so the first incoming request is 0. We are going to look at the numbers 0 and 0, so this has to have an index of 0. So we put the validated bit as yes, because now we have information in this index, in this location, in the cache. And then our tag is going to be 000. So the data that we store is all the data we have in the memory address 0. This was a cache miss, so I have to add it here. It's a cache miss because there used to be no data in this index. So the next request is 8. Since 8 has the index of 00, it has to overwrite the previous data here. So it's a cache miss and it must overwrite. Now I put the data from the memory location 8 into my cache in index 00, and the tag is going to be 010. And then my next request is going to be 0 again. So since it has to go into index 00, since last 2 bits are zeros, the data is going to come here. It's going, since it did not exist here, memory location 8 was here. we have to overwrite that, so it's a cache miss. So we are going to put memory 0 back into this index again. And then my next request is going to be 6. 6 is going to have the index 1 and 0. It does not exist here, so it's a cache miss. But I do not have to delete anything here because now it is going to go to index 1, 0. So I changed the validity bit to y, and then the tag is going to be 0, 0, 1. That is the first 3 bits of 6. And then all the data in memory location 6 goes into the data area. And then my next index is going to be 8. So my next request is going to be 8. So I'm going to bring that from the memory. It has to go into index 0, 0 again, but memory 0 is here. So it's going to be a cache miss, and I have to overwrite memory 0. Now I put memory location 8, the data in memory location 8 into index 0, 0, and I have to update the tag again. So as you can see, direct memory is going to provide me with 4 different indexes in this given scenario because I have 4 blocks available to store. But the problem is that I may need to overwrite things that I may be using later. So associativity helps with that, but associativity means that each of my indexes will have multiple blocks in them. So we call these indexes now sets because they keep multiple blocks. In a two-way set associative cache, I'm going to have 2 words or 2 blocks per set. So the initial state would look like this. I can still keep 4 different blocks, but as you can see, I am going to be addressing them with 2 different numbers, 0 and 1. So that means that my numbers 0, 6, and 8 are going to have only their last digits as their indexes. All the rest of the memory address, the 4 bits at the beginning, are going to become tags. So let's start our example with this given setting. The first request is going to be 0. Since everything was empty, I'm going to put it into 0. As you can see, the last bit here is 0. So the index it has to go into is 0. So I'm going to change the validity bit to y, and I'm going to put the tag as 0, 0, 0, 0, and all the data in memory location 0 goes into the data area. So this is the cache miss, and I'm going to add the data here. The next value that's coming is 8. 8, as you can see here, has the last bit of 0. That means it's also going to go into index 0. And its tag is going to be 0, 1, 0, 0. So when I look at here, I still have 1 more block available. So I don't need to overwrite anything. What's going to happen is that I'm going to just put the data in memory location 8 into index 0, and I'm going to update the tag for this. Now, if I need it again, I can access it. So the next request is going to be 0. 0 already exists in index 0. So it's a cache hit. I don't need to do any more action. I can just read this data and send it to the CPU. And then the next request is going to be 6. 6 is going to have an index of 0. This is the last bit. So it has to go into index 0 area. So it's going to have to remove something. What's going to happen is that it's going to overwrite the least recently used data. In our example, 8 was least recently used, so it has to overwrite 8. And so that I am going to update the data, and I'm going to update the tag. And then the next request is going to be 8 again. This means that the least recently used data has to go away again. In this case, 6 was the most recently used uh, data that came into the cache. So I have to remove memory location 0, the data of memory location 0. So it's going to update the memory location 0's data with memory location 8's data, and I'm going to change the tag also for 8. Okay, as you can see, we still needed to overwrite information. We can make it more associative. For example, if a cache is fully associative, it's not going to have an index. So I have 4 words or blocks per set, and I only have one set available for me in this fully associated case. So what I can do here is that I can start adding data with 0. 0, since everything was empty, I can just put this data here and write the tag at 0, 0, 0, 0, 0. That means 5 is all the address here in the tag area. And then the request 8 comes along, so I'm going to have to go to the memory, grab the memory location 8's data, and bring it into the cache. I still have available space here because I have 4 blocks of an area available for me. So I can actually bring in 2 more blocks here into the cache. So the next request is going to be 0. It's going to be a cache hit because it exists. One thing that I am going to emphasize here is that when it is a fully associative cache, you have to search through all of the information in the cache until you find the correct tag. This can take time based on the size of the cache, but in this case, we have only 4 blocks, so it shouldn't take much time. Again, the next request is going to be 6. 6 is going to be borrowed from the memory because it does not exist here yet. So it's the cache miss. So I'm going to add its data here into the cache. Next request is going to be 8. It already exists in the cache, so it's a cache hit. As you can see, fully associative cache can accommodate all the data that I need for these requests. But think about a case where I make requests for 0, 1, 2, 3, 4, 5, 6, 7, 8. In this case, I would need to overwrite data. I would need to overwrite the least recently used data. And every time I would need to go over each one of the entries to check if my data is in the cache. That can be very time consuming, even though caches are on the CPU and they are really fast. When there is a large cache, this can become an issue.